Hello and welcome to one of the first linear algebra videos I've made on this channel. Today we're going to be looking at whether a certain vector is in the span of another. And we have an interesting case today. I've drawn out, I did forget one minor detail. Oh wait, that's C. So I did draw out the vectors in R2. So we'll go ahead and say that this is in R2. This is in a two-dimensional space, R2. And you can see that we have a vector u1, which is equal to, has 2 and 1, and then 4 and 2 for u2, and finally c is negative 6 and negative 24. And so what we can say here is there's a relation between u1 and u2 such that 2u1 is equal to u2, meaning that if we multiply 2 by u1, we should be able to achieve u2, right? 2 times 2 is 4, and 1 times 2 is 2. And so 2u1 equals u2. And so if we draw this out geometrically, which always helps, we notice that we have a line. We have u1 and u2 both on the same line, like right here. It's not really shown for some reason on the video, but you can see that u1 is on top of u2 because u2 is equal to 2u1. So they're on the same line, which means that, let's say we want to achieve C, which is all the way right down here. This is C. The orange line is C. And so if we want to achieve C, how would we do that with the span of u1 and u2, right? Because u1 and u1 and u2 is just a line. So we can really only do, like if we do 3u2, 3u1, we're going to be somewhere around here, right? And it would be 6 and 3. And that would be like more like somewhere around here. But you get the point. It's not to scale. Um, and if we do negative 1000 u1, we're going to be all the way over here. But we're still going to have the same slope on this line because the derivative of a line x is equal to 1. Or I should say, sorry, the function f of x, which is some line, has the derivative of 1. And so it has a constant um, slope. And so we can never actually achieve c. And so just by this geometric description of the question, we know that we can't achieve c because the line will only go this way. We can never go down to c because the slope is consistent. It's not as complicated as I'm making it out to be, but there's a way to do it geometrically, or sorry, algebraically. So let's say we have the augmented matrix of we're gonna have the augmented matrix of u1, u2, and we want to solve for some x of c, right? And these are all vectors, mind you. And so we have our coefficient matrix A, which will be equal to 2, 1, 4, and 2. And then we have C, and then we have X, sorry, which will be equal to x1 and x2. And then we have C, which is going to be equal to, so this times x1 and x2 for some x1 and some x2, hopefully equals negative 6 and negative 24. And now we know that, I'm going to go ahead and erase this fact now that we've already used it, but we know that there does not exist an x1 nor an x2 in order to achieve negative 6 and negative 24 with the coefficient matrix that we have because of this whole slope example I just gave, right? And so, but how do we prove this instead of just looking at lines on a graph? Well, let's go ahead and augment this matrix, like what we see here, but with the actual coefficients. So now we're going to have 2, 1, 4, and 2, and c will be negative 6, negative 24. I'll put a bar here just to indicate that this is the rightmost column of the augmented matrix. And so let's go ahead and apply some elementary row operations in order to determine whether the system is consistent or not. If the system is consistent, meaning we have a pivot position in every column, such that it looks like this. Or we have something like we have a 0 in the rightmost column of the augmented matrix, like this. Then we're looking good. We're Bing chillin', as some would say. So what we want to do here is we want to scale row 1. So we're going to do 1 over 2 row 1. And then, so this is going to give us 1, 2, and negative 3. And then we're going to write down the rest of the thingy-majiggies. 24, cool. And the reason why I put an equal sign is because they are equal. Any row operation is reversible, meaning it's equal. And so now let's go ahead and do negative row 1 plus, I shouldn't have put this to the power here, I should put this as a subscript rather than a superscript, plus row 2. And so we're going to have the same top row, like this. But now we're going to have 0, because negative 1 times 1 plus 1 is 0. Same thing for 2, we're going to have 0. And then here we're going to have negative 21, because negative 3 times negative 1 is 3, and 3 minus 24 is negative 21. And so now we have an issue. We see that 0 equals negative 21, which we know is not true. 0, in fact, does not equal 21, negative 21, nor 21 for that matter. But our system is saying 0 equals negative 21, which is impossible. So it's essentially saying that with C, we are not able, with the span of U1 and U2, we are not able to achieve C. Now, if we had U1, U2, and potentially a new vector, U3, which we'll say is equal to, negative 1 and 1, which would be somewhere out here, then we're going to be able to find our system will be consistent for these vectors, because we can somehow get to C by using the 3 vectors we have available to us. So we could do minus, let's say, I don't know, U2, and then you do minus U3, and then minus U2, and then you could do like 1/2 U3. Let's say that gets us here, and then we do U1, which maybe gets us there. So we kind of went from like this to here, to here, to here, to here, meaning that our 2 vectors spanned R2, meaning we can access any point in R2 regardless of where it is, as long as our 2 vectors in R2 or in our set are linearly independent.